Imagine this, a single, elegant equation that could describe our entire universe. Everything, from the first fiery moments of the Big Bang to the very end of time. That's it. That's the ultimate dream of physics, the grand quest for what we call a theory of everything. And we're about to dive into this incredible journey of ambition, triumph, and you'll see some profound mystery.
You know, this isn't some new idea. The Marquis de Laplace captured this ambition perfectly more than 200 years ago. It's the dream of ultimate knowledge, right? Of seeing the universe's entire blueprint laid out before you. It's a goal that has captivated the greatest minds for centuries, and it's still driving them today.
So, what does this quest actually look like? Well, the main goal is to unite the four fundamental forces of nature we see around us. That's gravity, electromagnetism, and the strong and weak nuclear forces. The idea is to prove they were all once part of a single superforce that only existed in the superhot, high-energy chaos right after the Big Bang.
Okay, but if there was one superforce way back when, why do we have four today? The leading theory for this is called symmetry breaking, and Stephen Hawking had this brilliant way of explaining it. Picture a roulette wheel spinning really, really fast. The ball zipping around could be anywhere. That's kind of like the superforce. But as the wheel slows down, just like the universe cooled, the ball has to fall into one of the slots. Our superforce ball fell into four different slots, becoming the four distinct forces we know and love today.
So how do you even begin to prove something like that? Well, physicists decided to work backwards, right? Try to reunite the forces one by one. And this is where they scored their first spectacular success.
Now, at the normal energies we experience every day, the electromagnetic force and the weak nuclear force look about as different as you can get. One is carried by a massless photon and has an infinite range. The other uses these really heavy particles, the W and Z bosons, which gives it a super short range. I mean, on the surface, you'd never think they were related.
But here's the kicker. That's only true at low energy. Theorists predicted that if you could crank the energy way, way up, the field that gives mass to those W and Z bosons, what we call the Higgs field, would basically just switch off. And without their mass, they'd behave just like photons. All those differences would just melt away.
And you know what? They were absolutely right. In 1983, at the CERN Particle Accelerator, scientists created enough energy to see the W and Z bosons in action. And that discovery proved the existence of a single, unified electroweak force. It was a massive achievement, and more importantly, it was powerful proof that this whole grand dream of unification was actually possible.
So, with that huge victory under their belt, physicists set their sights on the next target. This one was even more ambitious, the Grand Unified Theory, or GUT for short. The goal here was to bring a third force into the family.
The logic for this was just beautiful. Experiments started showing something really fascinating. As you ramp up the energy, the strong force, the stuff that holds atomic nuclei together, it actually gets weaker, and at the same time, the electroweak force gets stronger. The math seemed to suggest that at some truly unimaginable energy level, their strengths would become equal. They would just merge into a single electronuclear force.
And get this, GUT came with this really cool bonus prize. The theory also predicted that in the earliest moments of the universe, the fundamental building blocks of all matter, quarks and electrons, were really just different faces of the very same particle, just another beautiful, elegant unification.
So, 3 forces down, 1 to go. But that last one, gravity, well, it wasn't just another step. It was a completely different kind of challenge. This was the final frontier, the ultimate boss battle for physics.
And this is exactly why. The two pillars of modern physics are just fundamentally incompatible. You've got Einstein's general relativity, which describes gravity as the smooth, predictable, continuous fabric of space-time. And then you have quantum mechanics, which describes the other three forces as a world of tiny, jumpy, probabilistic particles. They speak completely different languages to describe the same universe.
And this isn't just some philosophical disagreement. Every single time physicists have tried to write an equation that includes both, the math just breaks. It spits out complete nonsense like infinities for values we know are finite. It was a total dead end. To go any further, they needed a radical new idea.
And that radical new idea arrived with a bang. It was called superstring theory, and for a little while there, it really seemed like it was the answer, the key that would finally unlock the theory of everything.
The core idea is just incredibly elegant. It says that at the most fundamental level of reality, particles aren't little points. They're actually tiny, one-dimensional vibrating strings. So an electron is just a string vibrating in one pattern.
A photon is a string vibrating in another. All of reality, everything we see, is just a grand cosmic symphony played on these tiny, tiny strings.
And the initial promise was absolutely staggering. The math of string theory beautifully solved that infinity problem when you tried to include gravity. It naturally predicted the existence of the graviton, which is gravity's messenger particle, and through this idea called supersymmetry, it gave a clear path to unifying everything, all forces, all matter, into one beautiful framework. It really looked like the dream was finally within reach.
But, and you knew there was a but coming, right? As physicists dug deeper into the math, this beautiful, elegant idea started to unravel. It started revealing some truly bizarre and deeply troubling problems that you just couldn't ignore. The problems just started piling up. First, for the math to work, the universe needed 10 or 11 dimensions, not the 4 we see. So, where are the others? Theorists said they were compactified, curled up so small we can never possibly detect them. As our source author puts it, it's kind of like sweeping scientific dust under the rug. Then it got worse. Not one, but 5 different string theories popped out. A new idea called M-theory tried to unite them all, but it created an even bigger problem. It couldn't even predict why our universe has the number of dimensions it does. And that led to the theory's biggest problem of all. A number so staggeringly huge it's almost impossible to write down, let alone comprehend. 10 to the power of 500.
So what is that number? Well, that's the estimated number of different ways those extra dimensions could be curled up. And each one of those configurations would create a totally different universe with different laws of physics. So M-theory didn't predict our universe, it allowed for 10 to the 500 possible universes. And here's the thing, a theory that predicts everything ultimately predicts nothing at all.
This leads to a really devastating conclusion. A core principle of science is that a theory has to be falsifiable. There has to be some experiment you could do to prove it wrong. But since M-theory can just be adjusted to fit any observation, you can't ever prove it false. And for the author of our source material, that means it's just not science. He gives the M in M-theory his own meaning, teoria morta, dead theory.
So, after decades of brilliant work, of incredible highs and frustrating lows, where does that leave this grand quest for a theory of everything?
Well, the simple, honest truth is, we're still searching. A true theory of everything does not exist. Superstring theory, which was once the great hope, is still a fascinating piece of mathematics, but it seems to be completely disconnected from the real world. And that deep, fundamental conflict between gravity and the quantum world, it's still the biggest unsolved problem in all of physics.
Which leaves us with the most profound questions of all, doesn't it? Is a final theory even out there, just waiting for us to discover it? Or have we actually hit a fundamental limit to what we can know? Maybe the universe, in its ultimate nature, just isn't something the human mind can ever fully capture in a single, perfect equation. The quest, for now, continues.